dan Aplikasi, or JKSA. In English, we call as Journal of Scientific and Applied Chemistry webinar series. As additional information, JKSA is an open access and peer-reviewed journal published by Department of Chemistry, Diponegoro University, Indonesia. And this journal is published for every month, or we can say 12 times per year, and it will be published in the end of month. JKSA publishes research papers, review, and short communication in field of chemistry. JKSA itself has Sinta 2 accreditation based on the Ministry of Research, Technology, and Higher Education of the Republic of Indonesia. And although we accept the manuscript in Indonesia, however, we encourage all of the authors to write the manuscript in English, and in effort to internationalize JKSA and expand the reach of the readers, the accepted manuscript in Bahasa will be translated into English. So once more, we invite all of you, all the participants, to submit your manuscript to JKSA. Now, return to JKSA webinar series. Today, we have a great opportunity to learn chemistry from one of the experts, Dr. Alexandra Velian, from Department of Chemistry, Washington University, the US, with the topic of atomically precise nanoclusters as catalysts and building blocks for low-dimensional nanomaterials. Before we start the talk, I would like to ask Dr. Adi Darmawan, as in-chief editor of JKSA, for a short welcoming speech. So please welcome Dr. Darmawan.
Okay, thank you, Pak Basit. Assalamualaikum warahmatullahi wabarakatuh. Good morning for everyone, and also for Alexandra. Good evening. Today we have the ninth JKSA webinar, which is we are always held every month, and this is the first time for the someone from US to give a lecture, and we have 1 hour webinar, and I hope we can get great benefit from Dr. Velian, and because she is inorganic chemistry, and especially about nanomaterials. So I think this is a very great opportunity for us to learn about nanomaterial from her, and I think it's enough. And what already said from Pak Basit, I encourage for everyone to submit their research paper, the best research paper, to our journal, and I hope that this webinar can continue every month. Yeah. Thank you very much for Alexandra for joining us today, and your opportunity to give a lot of benefit for us. Thank you.
Okay, thank you, Dr. Adi Darmawan. So for all participants, I would like to inform the rules of the game in this webinar. So the talk itself will last for 1 hour to 10 a.m. So anyone who want to ask to Dr. Velian, please kindly write your question on the chat or raise the hand button. And also you are allowed to write a question in Bahasa Indonesia, and I will help to deliver it to Dr. Velian in English. Before we start the talk, I would like to share a short bibliography of our speaker, Dr. Velian. Dr. Velian gained her Bachelor of Science with honors from California Institute of Technology, Caltech, in 2009, while her PhD was awarded from Massachusetts Institute of Technology in 2014. Dr. Velian's field of interest are in catalysis, clean energy, inorganic chemistry, and materials. Her research group is pursuing the total synthesis of atomically precise inorganic nanomaterials for catalytic electronic and quantum information application. In 2020, she received the NSF Career Award funding work on elucidating and harnessing metal support interactions in single atom catalyst using designer nanocluster as functional models. Ladies and gentlemen, please join me in welcoming Dr. Alexandra Velian. Dr. Velian, the time is yours.
Thank you so much for having me and for the really nice and thorough introduction. Just to check, do you see the proper screen shared?
Yes.
Yes. Okay.
Okay, great. Okay. So yeah, thank you so much, Adi. Thank you so much, Noor, for having me today. It's really very exciting for me as well. I have never been to Indonesia, but I sure hope I will. I do drink a lot of coffee though. It's 7 p.m. here, so but don't judge if I am still sipping a nice cup of coffee to get me through. I have a 6-month-old, which keeps me awake at all hours of the day and night. Yeah, it's really a pleasure to be here, and so I look forward to telling you about this cluster work that was funded a couple of years back by the NSF. But before I do that, I thought I'd share a map. Probably, the one of the silver linings of this ridiculous pandemic is that somehow, we normalize these webinars, which means that we can connect so much easier. And I'm really thrilled about that, actually, even as I am here in the basement, not on campus with this beautiful background. But I thought I'd show, of course, you know very well Indonesia, and so I'm here on the other side of the world, really, in Seattle. So like Pacific Northwest, it's a really beautiful area, but I wasn't born here. In fact, I grew up in Bucharest, Romania, which is here. And then I went to college in the US and moved around the US. And then here I ended up all the way in Seattle. So it's truly an international world, and it's a real privilege to have been part of this academic community that enabled me to travel the world in a way that I would have never had the chance, considering, how I grew up. So here is the chemistry department at the University of Washington. To be frank, I have not seen this building in person in a year. So this is the chemistry building. We work here. It's a fantastic campus. This is the Rainier Vista. There's a beautiful mountain that thrones in Seattle that you can see, and just about now the cherry blossom are in bloom. So this is part of the campus where people gather and to watch the blooms. It's really beautiful this time of the year, and with a little bit of luck, I might even get to see it in person, but we'll see about that. Okay, so now on to the chemistry. I guess a core interest in our group is really to deterministically synthesize heterogeneous catalysts that have active sites which are atomically defined, they are tunable, and have a uniform distribution. And then use these catalysts to tackle some important small molecule transformations. I'm just showing here a few that you've probably seen, you're probably quite familiar with. There are a lot of interesting small molecules that we would love to transform into value-added products. I'm showing here carbon dioxide or carbon monoxide, of course, methane, nitrogen to ammonia. So, there are a lot of industrial processes that are already in place to turn some of these into these value-added products. For example, ammonia production, of course, the Haber-Bosch process is extremely successful. But what really connects all of these is that they're multi-electron transformations, they're multi-proton transformations, and we're behind at figuring out a way to selectively turn them into desirable compounds. And there's a lot of work out there to kind of crack this nut and figure out how to make better catalysts. And there are many different directions. Some of them are homogeneous, some of them are heterogeneous. We really like to think about the problem of how do you go about making a heterogeneous catalysts. And because these ones have some of these limitations that we want to address, and you don't really know how they work. And so they're really made using a trial and error approach. I'm showing here the the Haber-Bosch process to convert nitrogen and hydrogen into ammonia. So this process was developed well over 100 years now. And, in order to get to the final composition of the catalyst, which is pretty much what is in use today as well, there were many, many different conditions that were tried. So it really trial and error to get to something that works. And it's kind of like a black box. You don't really know why it works this way. And I'm drawing here a comparison that in a sense, the same thing happens in biological systems. Nitrogenase are found in anaerobic bacteria, and that's the way that, of course, naturally in the nitrogen is sort of taken from the air and converted into ammonia, which is critical to make food ultimately, fertilizers and then food. And so here's what the nitrogenase core looks like. But really, you can imagine evolution took a long time to come up with a system. So while the trial and error strategy has been quite successful to, for example, develop the Haber-Bosch process, it's really failed us to solve some of the other critical small molecule transformations. And so there's this school of thought that perhaps you could make in a more deterministic way a catalyst that you know what it looks like, and hopefully maybe aid that by computations or by other chemical intuitions to know what to target. And so not only that you could make this complex material, but you know what you should be targeting and making it. In my group, we are synthetic chemists, so we think a lot about how to synthesize those complex inorganic materials that might have active sites. And so this concept of active sites is really what it does. It reflects experimental evidence that many catalytic surfaces are not uniformly catalytic. So they have some special sites where atoms are distinguished by a special chemical coordination or composition, and they are the ones doing the work. And in fact, this was proposed by a chemist 100 years ago, well before there was significant experimental proof that that was the case. But of course, further studies showed that that was in fact true. So one of the interesting things about the presence of active sites is that, the fact that they exist means that the size of the particle actually matters in terms of the activity of a catalyst and also its selectivity. And what I'm showing on this slide is are two studies that I absolutely love because of how clearly they show exactly that point, how size affects reactivity and how and as well as actually, as it turns out, selectivity. So molybdenum disulfide is a metal chalcogenide that has been known for a long time. It's an excellent catalyst for hydrotreating. And it turns out that the crystallites that are most active in this transformation are single layer molybdenum disulfide flakes. So this means that literally you have a single layer of molybdenum sulfide. It's a layered material, and we see here a projection of what it looks like at different dimensions from top down. And so typically the most active crystallites are 2 to 3 nanometers in size. So that's pretty small actually in operating conditions. And so what was discovered is that if you add even just a little bit of cobalt or nickel or other metals, as it turns out, what happens are a few things. One, you increase the activity of the catalyst by more than an order of magnitude. That's a lot. So something funky is going on there. And then importantly, you also change the selectivity of the reaction as you switch from cobalt to nickel. So the two additives that you promoters essentially yield different products at the end, different selectivity for the products that are formed with respect to hydrotreating. And so I guess the images that are shown here, these are SDM. So you really image a single flake and then see what happens in operating conditions. Where are these active sites that exist, as you perform the reaction? For example, you abstract a sulfur from a petroleum product, which is, kind of an important, this desulfurization is an important transformation. And it really enables us to get an atomic level understanding of what happens at the active sites and how this transformation is done, which in turn, might help us think about how to make better catalysts for all sorts of other transformations. So let's take a look here. And as we move from the left to the right, these flakes of molybdenum sulfide, they're really extremely small. They're single layer, and then they're also just a few atoms large, right? So they're really molecular dimensions. Of course, they are on a wafer, so they're isolated flakes. You can't really scale this up and put in a bottle. And still have the same kind of precision in how the flakes look like. So, but as we look at what happens during the reaction, we see that the active sites, which are indicated by these arrows, are positioned in different places on the flake. And so in the small sizes, they're at the corners of the triangles, whereas as we look at the larger ones, they're on the sides. And that really affects it's one of the reasons why the selectivity is different as you go to different size flakes. Because the sterics are different, the electronic properties of those sites are going to be different. And on the right side here, what I'm showing is that a separate study in which the authors asked the question of, okay, if you put that cobalt and nickel on this molybdenum sulfur flake, where does it go? Because perhaps we can identify where the active sites are in this mixed material. And it turns out that the cobalt in this case and same thing with nickel, it's really localized on the edges. So it doesn't really insert itself in the base of the flake, although there's some cobalt atoms that are going in there, but most of them are on the sides. And so we really love this study because it's very hard in heterogeneous materials to get that kind of precision in understanding what happens. And so what we thought is, hey, what about making a molecular version of this that you could really put in a bottle, that you could study with all the tools that we have available to us as molecular chemists, and then perhaps develop new catalysts for different transformations that really rely on this interaction of the active site, for example, cobalt, with this non-innocent support, which is a metal chalcogenide. And so to do this, we thought that we could easily take an existing cluster. So I'll walk you through the scheme. It's a little bit complex, but really what it is, it's a molecular cluster that has been known for a long time. It has an octahedron of cobalt atoms that is encased in a cube of chalcogens, and the chalcogens are selenium atoms, okay? And so if you view this cube down its C3 axis, now you can see it projected here, okay? But what we thought we would do is use this as our core, kind of analogous to that molybdenum sulfur flake, and then use capping ligands to provide a surface coordination site for a different kind of a metal. And then we can have, in a very controlled environment, this interaction between the support, the cobalt selenide, and the surface side that is there to interact the way, with the core and see how that compares with this heterogeneous catalyst that I was describing earlier. So we use an aminophosphine to do that. We cap the cluster with it, and it turns out that that amine, upon deprotonation, enables these 3 coordination sites on the surface of the cluster. So I have 1, 2, and 3, and we can install using deprotonation and then treatment with a metal salt, a really wide range of metals. We only looked at the 3D series, so chromium, manganese, iron, cobalt, nickel, copper, zinc, as well as zinc, and then also tin, so going beyond the D metals. And we can do this in fairly large yields and scale. And so what I'm going to tell you about today is what we learned from studying this system. Okay, so we asked a number of questions that help us understand mechanistically, well, is this a functional model for an active site in, you know, in a heterogeneous material, and how does it work, and its electronic structure, and is it a catalyst? And also importantly, I'll loop back at this question of, can we use this to build nanomaterials as a building block for that? So I'll touch a little bit on all those points. And so I'll start off with questions about how do we understand this metal and support interaction, so the interaction between the edge metal and the cluster core, and the factors that affect it. So metal identity, something that we call allosteric effects, the overall oxidation state of the cluster, the identity of the substrate, and the ancillary ligand. And so I won't describe all of these in detail because of time, but I'll touch upon some of them. And then I'll show you that, in fact, the edge sites are catalytically active in one transformation that we uncovered thus far, and then look back at nanomaterial synthesis. Okay, so you know, we have some of our work. We're a fairly new group actually, but some of our work is in the literature, so you can refer back to it if you're so inclined. Okay, so this is a complex slide. Let me walk you through it. The first question that we want to understand is this interaction between the edge metal and the cluster core. And everything I'm showing you here, these are single crystal structures. So, you know, we know exactly where the atoms are positioned within our clusters. So although they're kind of like nanoclusters, we can really characterize them with atomic precision. So they're atomically precise clusters. So let me draw your attention to this new center structure. It's complex, but I'll walk you through it. It's this cluster core that I showed you before, the cobalt selenide, the cube, seen down its C3 axis, and then with 3 iron ions installed on its surface. Okay, so overall the cluster is in a neutral oxidation state. And let's take a quick look at what the edge site looks like, the connectivity there. So here's one iron site. It's coordinated in this case to an isocyanide. In fact, the stretching frequency of the cyanide group tells us that the iron is extremely electron deficient. And if we look here, so the iron is anchored to the cluster surface. I'm only showing 2 cobalt atoms and 2 seleniums for simplicity. Okay, so it's a snapshot of this one site. And the iron is anchored to the cluster by 2 amides that have been deprotonated, aminophosphines. Here they are. And what was really cool when we got this first structure was to see that there is indeed an interaction between the iron and the selenium core, because that was important because we really wanted to emulate that kind of, you know, we were aiming for a hemi-labile interaction between the metal and the cluster, and that's just going back to this idea of this low coordinate sites that are active sites in catalysis. So you don't want a saturated metal because then it cannot engage with a substrate. So this was really, you know, encouraging to us because there was a substrate, isocyanide, coordinated to the metal, and at the same time the metal had one interaction with the surface selenium side. But not with the other one, okay? So it's only binding to one of the exposed selenium in that coordination pocket. Now, what was really cool to see is that if we take this metal, this cluster, and then we oxidize it, the way the metal, the edge site engages with the cluster support changes. And it doesn't just change because we introduced a chelating ligand. This is a phenanthroline. Okay, so this is a chelating ligand, so you would expect it to interact stronger with the iron and chelate and pull it out perhaps of that pocket. But that's true also for other ligands, including, you know, monodentate ones, that essentially what you do upon oxidation is you alter dramatically the interaction between the iron and the selenium. So you no longer have a bonding interaction between the iron and selenium upon oxidation. But conversely, if you reduce the cluster, and again, we can isolate these, which is really helpful because you don't have to guess, hey, what exactly do I have in this, what is this compound? We can cleanly produce and isolate the molecular species as monooxidized and monoreduced. And so in the reduced case, we see the opposite. Now, the iron has no affinity for external ligands. So every ligand that we've exposed to this cluster, it no longer binds to the iron. The iron is just completely engaged with the 2 selenium. So we have 2 selenium iron interactions, 1 and then 0, and that's switchable by this redox in this redox series. And what this sort of hinted or foreshadowed for us is that the electronic structure must be such that essentially when you take an electron out, it's coming out from the cluster core, and when you put an electron in, you're probably also putting it into the core. So then the seleniums become less electron rich than the iron is. Prefers to bind to external ligands, or the cluster becomes more electron rich. The seleniums are better ligands, and then they outcompete external ones. And so, to probe that in a little bit more detail, we can, for example, start with a Uv-Vis spectroscopy. That's a nice way to probe any electronic transitions that occur. And what I want to draw your attention in this plot is the following. So in the dashed line, what we have is just the cluster, the cobalt selenide cluster without the edge sites, okay, no irons. And so that's the dashed line. And then if we add the 3 metals, we see this increase in the absorption, and also a red shift and this tail, absorption tail. It's but then in pink and in blue, what I'm showing is essentially the difference between having those iron selenium interactions or not having them. So we think that obviously there are other things going on here, but we think that this red shift essentially in the going from blue to pink is associated with having these iron selenium interactions. And it's kind of cool to see that they're associated with an absorption at such low energies, even if it's really hard to interpret because it's not a nice Gaussian. But to really dig into the electronic structure, what we used and the reason why we started with iron edges is electrochemistry and mass power spectroscopy. Okay, so on the left is electrochemistry. So I'll walk you through it. The reason why we really love this cobalt selenide cluster is because among other things, it's very stable to taking and putting electrons in. It changes very little geometrically, so entropically it's quite robust, and you can really cycle through many electrons. So like 1, 2, 3, 4, 5, 6, and they're all like chemically reversible. So the traces are measured in 2 different solvents just to enable us to probe oxidation, which is on the right side, and reduction. Okay, so the neutral cluster is here. This is the first oxidation, second, third, fourth oxidation, and then this is the first reduction and second reduction. Now, what happens if we put the irons and have these irons on the surface of the cluster? How does the electronic structure changes? And there are a couple of things going on. One is that a lot of the features stay pretty much the same. Like, for example, the second reduction and some of the oxidations seem to resemble very nicely the cobalt selenide core. However, the most drastic change occurs in this first reduction event. So the first reduction, which we use as a proxy for the lowest unoccupied molecular orbital, so the LUMO level, is really stabilized by the iron selenium coordination. Okay, even if we are pretty confident that the LUMO as well as the HOMO, the highest occupied molecular orbital, are both localized on the cobalt selenide core, the LUMO is really stabilized by this. It's as if the iron is removing electron density from the selenium, kind of like a Lewis acid might, and then it's easier to put an electron on the core as a result of that. That's sort of a hand-wavy, intuitive way to think about it. The other thing that is happening that we can read from this electrochemical study is that if we change what ligands are bound to the surface, then we might be able to pinpoint where is the iron 2 to iron 3 oxidation. In its neutral state, we know for sure we start with iron 2. And the question is, at what point do you oxidize the iron 2 to iron 3? And can we see it? And so if we, for example, have an isocyanide coordinated to the surface, we should see, we thought, a difference between a case where we don't and the one that we do, and the oxidation event that is associated with that iron site should change the most. And what we see is that this third oxidation responds by changing by half a volt when we have isocyanide coordinated to it in the way that you would expect. And so we think that this is associated with the iron oxidation. So the iron states are really buried in there. They're not at the valence level, the HOMO-LUMO, which we think is here. And if we couple this with mass power spectroscopy, which is shown on the right side, and what you want to take a look at here are two things. One is the position of this the isomer shift, and that's really the most indicative with the electronic structure of the iron. And if we look at these numbers, if we go from the mono-oxidized to the neutral state to the mono-reduced, this value doesn't change significantly. You're still really around 0.6, which is indicative or associated with an iron 2, not with an iron 3. So this sort of confirms what we thought, that the HOMO and the LUMO levels that you probe by oxidation and reduction are localized on the cobalt and not on the iron sides. And so we can do this kind of analysis, and we do it for all other derivatives. And so here's just a snapshot of how this HOMO-LUMO gap changes in the series. And the reason why the HOMO-LUMO gap is important is because it really tells us about the reactivity of the cluster. If you have a really large HOMO-LUMO gap, then that's typically associated with very stable molecules, right? So sodium chloride has a very wide band gap. Whereas, here we want to see something that is shrinking in its value from the naked cluster. So here's the naked cluster. It's a 1.4 UV. That's fairly large. But what we see upon metallation is that this band gap, again, we estimate this from electrochemical measurements of the HOMO-LUMO, the first oxidation, first reduction of the cluster core, that this sort of gets smaller with the metal, so going from chromium and all the way to tin. And in most of these cases, what we observe are a few things. One is that the HOMO level, which we think is again local, the first oxidation of the cobalt core, doesn't change that much. But what we find is that the LUMO does respond to the strength of the of the metal selenium interaction. The stronger the interaction, the more this is stabilized, and then the band gap gets smaller. And so here it is for an iron. There are a few other effects, but in the interest of time, I won't go into them. We can change the ligands capping the cluster, and then we can tune the electronic structure using that as well a little bit. But there are a couple of systems here that behave differently, and I'll spend a couple of moments to tell you about them. So the tricopper, the HOMO-LUMO gap is very small, and we can see that it's just something funky is happening here. And same for the tin, and I'll tell you a little bit about that. So to kind of understand what happens with the copper, I'll tell you how we simplify this question by essentially installing, instead of 3 edge sites, a single one. And what this enables us to do is just have a little bit of more control over what we're looking at, and simplify the question a little bit. So we can use synthetic chemistry to isolate this series. And so here's a single iron on the cluster, a cobalt, a copper, and zinc. And we can use electrochemistry to probe them, same way that we did before. And so I won't go into all of these details, but but the cool thing is that now we can calculate these clusters, the electronic structure of these clusters. And we actually find that a little bit surprising to us. These are complex systems, a lot of metals there, open shell, many of them. But what we see is that the calculated HOMO-LUMO gap matches fairly well the experimental values is that, and we see the same trend of the LUMO being stabilized the most. But what's happening with the copper? So on the left, I'm showing you a calculated spin density plot. This just tells us where the unpaired electrons are. Well, they estimate, they're calculated. And so I want to draw your attention to the copper system. So here's the copper, and in its neutral form, we start off with copper 2. So copper 2 should have an unpaired electron, but the spin density tells us that it does not. But now that the cobalt core, which is diamagnetic, no unpaired electrons in its neutral state, has some electrons localized on it, spin density localized on it, and in a very anisotropic way, which is also kind of interesting. And so what this tells us is that most likely what happened, the copper 2 has oxidized the cobalt core, and now my HOMO level and my LUMO level are different than for the other ones. Okay, so the HOMO level is this copper that is now copper 1. So if you oxidize it, you pull an electron from it, and then the LUMO level is now the oxidized cobalt core, not the neutral one. And this is also confirmed by what we see when we in a silico oxidize the cluster. We see that in fact now we do observe spin density on the single copper. So that's just sort of to give you an idea of how we can actually play with, by changing just the edge site, we can tune the electronic structure of our system. Here's another strategy to do that. We thought, okay, so if we one way to take a wide bandgap semiconductor and introduce and change its electronic properties is to dope it with something that is redox matched with its band gap. So we applied the similar strategy here, and we took tin. If you look at where tin 4 to tin 2 reduction might occur, you see that it overlaps really nicely with the band gap of our cobalt core. And we set out to do it in the lab and found that, our hypothesis was confirmed. So here is the synthesis of the tritine cluster. The tin is now, it's a dialkyl tin, which is again anchored by the two amides in the way I'm showing you here. Beautiful Nmr spectroscopy because you have tin, phosphorus, selenium, proton, carbon. So really nice NMR. I'm showing here a snapshot of the edge site only. This is again single crystal X-ray diffraction. One thing to note here is that the tin of all the compounds we made is the only one that does not have binding interactions with the selenium, even if tin 4 coordinated to 5 or 6 atoms is actually quite common. But let's test our hypothesis, and what we see here on the left is the electrochemistry of this cluster. And so in short, here's the first oxidation of the cluster, second, third, and how it compares to the free ligand. And now, compared to everything we've seen before, check out these two closely spaced single electron reductions that essentially, we believe are associated with a tin 4 to tin 3 and tin 3 to tin 2 reductions. And it was kind of surprising, but in a good way to us to see how that they are still chemically pseudo-reversible. But now we have a LUMO that is localized on an edge site, so no longer on the cluster core like all the other metals. So another effect that I want to make sure that I'm making good time, that we were wondering about, that relates again to how these nanoclusters react and how they relate to heterogeneous systems, is what happens when you have a binding event at one surface site? How does that affect binding events at the other two sites? Okay, are they the same or not? How do they communicate with one another? And that's an ongoing investigation, but I will show you one quick story to tell you what we've learned. And so if we now go all the way to zinc, what we see is that in the neutral form, here's the zinc cluster. I simplified the cluster core as this teal cobalt cube. And the three edge sites that are either pulled out of the coordinating to the cube by phenanthroline. So here are two of the zinc sites are completely pulled out, not interacting with the seleniums. And then the third one is really coordinating to seleniums in this kappa 4 coordination mode. And I depict this as an off state. But what was really cool is that now, not only that we have the site differentiation essentially of the edge sites, is that if you oxidize these, now you turn on this site and now it can engage with external ligands. And so one way that we can kind of put this to work is to show that we can actually control the dimensionality of assembled materials. So if we start off with this as a building block, we can make a wire. And we do. This is again from single crystal X-ray diffraction in its off state. But now if we oxidize it, we give rise to the formation of two-dimensional nanosheets. And so here it is, this sort of redox switch enabling us to control the dimensionality of atomically precise materials. And I'll loop back to this idea in just a little bit. But I wanted to segue into telling you that these edge sites are in fact catalytically active. And what we've looked at this far is the activation of azides with isocyanide. You might remember the iron was coordinated in its neutral state to isocyanide, and it wasn't, it was because of this transformation that we were interested in it as a ligand. It's a nice way to follow spectroscopically what happens, but it turns out the tri-iron cluster is an excellent catalyst for this transformation. It happens at room temperatures in just 3 hours, and out comes this carbodiamide, which is not an unvaluable product in itself. And then what was especially interesting is that at the end of the reaction, our catalyst, I'm showing here the NMR before and after, and labeled in red is our catalyst. The paramagnetic features associated with it, and we actually see no decomposition of the catalyst, and that's kind of cool because, well, it's a little bit unexpected, and it just gives us hope that we do in fact have these edges as catalytically active sites. And it's not trivial to probe whether that's the case, because the transformation is so fast that we're just unable to see intermediates and isolate them. So to tackle this, what we did is simply, we thought, hey, if we switch the edge site with some other metal, we might be able to slow down the same transformation. And in fact, that's really the case. If we go from iron to chromium as the edge sites, 3 chromium sites, now we slow down the catalysis. This is just percent conversion versus time. And what this metal enables us to do is to isolate and characterize, these are X-ray structures again, the catalytically potent intermediates in this transformation. And so answering this important question of, are all the edge sites catalytically active? And so here's an instance where a single edge site is binding to this nitrine, which is essentially our catalytically competent intermediate to then react with isocyanide and form carbodiamide. And then at 2 sites, and then at 3 sites. And that's just showing the connectivity here of this nitrine bound to the chromium surface. And so I want to make sure I'm staying within time here. This system is something that we are currently studying, and we're very excited about it because also it has this amazing electrochemical profile. So electronic structure that we can probe electrochemically, and we can in fact go from reduce what we think is the chromium nitrogen multiple bond and once, twice, and 3 times. So we're hoping the system is going to answer important questions about how the edge sites respond, and how is transferring the first nitrine different from the second to the third, because that might answer this question of allosteric effects on the cluster surface. So I think maybe I still have 2 minutes here, so I'll just I'll tell you, I'll kind of close up this presentation to, I hope I showed you this far how we can really use as magic tricks, these edge sites and swap them out to attain different functionalities. And I'll just show you one more. And what this slide really is to say that, look, yeah, sure, we love studying the mechanistically and what happens in these nanoclusters, but we would love to make ultimately heterogeneous materials that have this type of functionality in the same way that, I'm making an analogy here. We go from, this is sort of how I think about the state of inorganic synthesis. We would want to make these sophisticated structures that are functional, kind of like a Lego city. But what we can do right now in the lab looks more like this, which is what my skills in Lego building are. Maybe we can make something more fancy like this, but something that really embodies this function through structure paradigm, we have yet to get there. And that's sort of in contrast with organic chemistry, where you can take these what are called privileged starting materials, like terpenes, if you will, or in this case, resveratrol, and build a very complex organic structures that are also functional, that serve a function. And so we really want to tackle that in inorganic synthesis, and we want to put our clusters to use in that sense. And so as a last example of how we can swap these edge sites to achieve a function that we target, I'm showing here the Tricobalt cluster. So essentially now you have cobalt on the core and cobalt on the edges. And the reason why we swap to it from other metals is because now the cobalt binds more strongly to other ligands, for example, a pyridine. And we thought, I'm showing here on the right side, just the crystal structure of this material, but of this molecule, in which you can see that the cobalt binds 3 pyridines more stably than the iron, which has a lower affinity for ligands. And we thought we can harness this to build nanomaterials. And in particular, we were targeting 2-dimensional nanosheets. So here we have 3 attachment sites, 1, 2, and 3, and we thought, okay, so it's kind of like a triangle. We should be able to get a nanosheet out of it, and that's exactly what we did. We took this linker that is linear and ditopic to the 2 points of contact, and at the end, we form a family of materials. This is just a snapshot into the single layer. They are all layered materials. They're all van der Waals materials, and they're 2-dimensional. So what I'm showing you here is how we can really, not only that the materials can be characterized by X-ray diffraction, but if you look at their morphology, you can see this layered structure. And in fact, you can peel them off using mechanical, like Scotch tape, and then probe them. This is optical microscopy. This is scanning electron microscopy, and this is atomic force microscopy, so AFM, in the single flake. So after you exfoliate it with the Scotch tape, we can get very thin flakes of these essentially synthetic nanosheets. Think graphene, right, that you peel off. And so we'd love to take this to the next step and add functionality to these precise, atomically precise nanomaterials. Okay, so I'm gonna close off here, and I hope I showed you how we have this exquisite control by using this molecular strategy, and we have exquisite control not only over the function, for example, catalysis, but also over probing the structure-activity relationship, the electronic structure of this very rich in properties, nanocluster, and that we can ultimately use it as a competent building block to access synthetic nanomaterials with atomic precision. And of course, I want to conclude by thanking my group. I have a phenomenal group of students. So the ones that really did most of this work are Jonathan Caphart and Ben Mitchell, as well as a former postdoc, Andre Kirilla, also some undergraduate students that we work with. Catherine Romero in particular had an important contribution here. And our collaborators and funding. And of course, thank you again for your invitation. And maybe I will chicken out and not say this out loud because I'm not sure I know how to make maybe terima kasih. Thank you for having me here. And I'm happy to take any questions.
Okay, terima kasih Dr. Velian for the very interesting presentation. Now we have like a lot of questions for you.
Excellent.
Thank you. So first question from Pak Adi Darmawan. So you present a lot of structure of your complex, and then could you like explain the characterization of this complex? How do you carry it out? Because like how to get the definite structure from your complex?
That's a very good question. And so our lab really spans the techniques that we use to characterize the materials. We make really range. But the molecules I showed you, we treat them as molecules. So first of all, we're gonna isolate them. We're gonna make sure to take an NMR, a proton NMR. We're gonna take a phosphorus NMR and any other nuclei that might be helpful in characterizing them. We do elemental analysis to make sure we get the element ratio that are present in there. And because they are so, we really love to look at their structure, and because they're crystalline, we're able to really peek at the atomic positions. And so all these structures I showed you, those are X-ray diffraction studies of single crystals. Okay, so that's you can really see most of your atoms and in there. Probably not the hydrogens, we calculate those, but they're single crystal diffraction. And in addition to this, you saw a lot of electrochemistry because they're so beautifully robust in cycling through different oxidation states, Uv-Vis spectroscopy, IR, infrared spectroscopy. We use all techniques to essentially probe and understand different aspects of their electronic structure and properties, as well as, of course, reactivity. So we look at that as well to probe them. But very molecular, mostly molecular, except for at the end where I showed you these mechanical exfoliation and so more nanomaterials.
Okay, and following to that question, I have a question for you. So sometimes it's so painful to get like a single crystal, because when I did in University of Glasgow, sometimes I get a very nice crystal, but oftentimes I fail to get it. Then do you have like a suggestion how to get like a good single crystal?
Yeah, that's an excellent question. So I was pretty much in every lab I've ever been in, we refer to crystallizations as kind of like magic, because you just don't know how to really get the perfect conditions. But there are a few things that you can do to increase your odds. Okay, so I always tell my students, first of all, make sure you set up the crystallization, because if you set up no crystallization, your chances are exactly 0 to get crystals. Although that's not always true. Sometimes you get lucky and you get an NMR cube with a crystal in it, but don't rely on that. So it's like strength in numbers. I think if you prepare a saturated solution of your compound and you filter it to make sure no particles are present there, you have your compound pure, then you're going to find this scenario where you have a solvent and maybe an anti-solvent you let it like kind of sit in this mixture for a while until you see if nothing comes out, you're probably not at saturation. So you need to add a little bit of a different solvent or increase concentration, or maybe put it in the fridge. And then if stuff crashes out too quickly, then you probably want to slow down that process, and so on. But first and foremost, try again and set up like 20 crystallizations, or maybe more. And if we can crystallize proteins, we will certainly be able to crystallize these compounds as well, with a bit of diligence. Yeah.
Okay.
Fortunately, my students believe that and they do it, which I'm very grateful for.
Okay, thank you for suggestion, Dr. Velian. And then for the next question, how to control the cluster size during the synthesis process?
Yes. So because our clusters, so there are two parts of this question. We start off with the cobalt selenide core, and I think that's really the most of the self-assembly happens there. And this 6-8 cluster scenario, where you have this cube of chalcogens that encases this octahedron of cobalt, it's just a thermodynamically very favorable structure, and it just forms as the sole product pretty much, if you make sure that your stoichiometry is right, temperature is right, etc. So we don't really have to worry about that. In that sense, we're really more in the molecular world. It's not like you make these colloidal materials where you have to think about dispersion. And then to go from there to these anchoring these edge sites, we have these aminophosphines on the cluster that are poised to support one metal for two ligands. So that's the beauty of deterministic synthesis, where you use various chemical principles to guide your synthesis. Yeah. So then we obtain a single product as a result of that.
Okay, thank you. And then the third question, the topic is very interesting. However, it's quite difficult to be conducted in Indonesia.
Yes.
And then maybe some computational study might be possible. Then could you explain more with how you get or you study computational thing to support your data analysis?
Right. Yeah, very good question and very good point. I mean, the truth is that it is exactly right. This research can only be conducted in very specialized laboratories. And that was actually my own motivation to kind of come to the US, because I wanted access to labs that have those abilities, which I did not have in Romania at the time. Maybe things have changed. And so as far as, computational studies, well, I want to say two things, though. There are other systems that are a lot more accessible synthetically that one could tackle in less fancy labs, although the characterization, I guess, that can be tweaked around as well. But computationally, depends what question you want to answer. I know enough about calculations to know I don't know enough about calculations and DFT, and so I know just enough to be dangerous with it. And so we try to ask to put questions that are, if what we obtain by DFT doesn't match our experimental work, then we know we're not doing, the calculations are not valuable to us. So, I guess we did this HOMO-LUMO study, and then, we can match it with experiment. Okay, it looks good. Now we can believe the spin density, plots as a result of that. But that's, we don't go too much further into it, because these open shell systems are hard to calculate.
And as a bridge, have you ever calculate the difference between your, for example, voltammetric HOMO-LUMO analysis with comparing to the computational result? Have you ever tried to compare it?
Yes,
just
absolutely.
As information.
Yes. And so we do have, but only for the monometallated clusters. We have not yet been able to do that with the trimetallated ones, just because the calculations have not yet converged.
Okay, thank you. And then the next question is, everything is presented using the fourth period transition element. Is it possible to use the elements in the fifth or sixth period?
Absolutely, yeah. And we actually have some interest in looking at precious metals as well, and see how, what we can do in terms of reactivity. But I have a small group of people, and we started somewhere, and we started with base metals, because we harbor this hope that we could do interesting chemistry with these, with these base 3D metals that are less expensive.
Okay. And then how? It's quite
not very
similar.
Not very new. We have this fantastic postdoc that did the calculations, but it's pretty limited in terms of calculations. Yeah.
Okay. Then what is the major change in the properties with a change in structure of your complex?
So I would say the stabilization of the LUMO level is a drastic change in the properties, as well as the reactivity. No active sites on the surface, no catalytic activity. So
okay, that's the important point, right, for this catalyst.
Yes.
Okay. And this is important question. What is the key to a successful synthesis process?
So I think the purity of your starting materials and just, I guess I tell my students, set up the reaction to win, right? Don't be sloppy, be thorough, do your best you start off with a clean compound and you can control what happens. So you only change one parameter at a time when you seek to target the transformation.
Okay. Is there any more question, Pak Adi? Oh yeah, and what is the instrument used for the measurement of current potential? Is it cyclic voltammetry or?
Yes, correct. We used primarily cyclic voltammetry and to do this. Okay. Yeah.
Mm-hmm. And what is the condition? Do you use like under nitrogen, or also using like the carbon, or?
We use it inside of a glove box, actually. So it's easiest for us to bring it inside of a nitrogen glove box, and then we protect it from degradation, because the compounds we work with are not water or air stable.
Okay.
Yes.
And this is another question. So he want to ask more about the voltammogram on slide number 11. So from Psychophonetic, it describes that how the Fa comes affects energetic stability on the cobalt complex, cobalt selenium complex.
Yes. So I would say that the iron really just, as I said, lowers the low, the LUMO of the cobalt core. That's like the energetically the biggest change. So you're sort of bringing that reduction to lower potentials.
Okay. Would you kindly elaborate it in electrons transport way so we can come to conclude the effect of the Fa existence in it? And secondly, if it will stabilize LUMO, what is the most affected?
So I wonder if I understand the question correctly. So
it's like you want to ask more how the effect of the Fa existence in the electron transport of your complex, I think.
Yeah, so the clusters, and these are molecular compounds. And so we do think a lot about electronic transport through the material, like in bulk. But most of these, because they are separated by the organic ligand shell, they are not conductive cluster to cluster to cluster. So we can, while we can cycle through different oxidation states within the cluster itself, we have not yet solved this problem of how do you connect, which is an important problem to solve. How do you connect the clusters together in a way that they communicate, and now you have like a wire or something like that. So they're not conductive in that sense.
Okay, and compared to the HOMO, so LUMO is the most affected, right?
Yes,
based on the properties. Then
yes.
could you like give a conclusion? What is the main effect that can change the LUMO most rather than the HOMO?
Yeah, well, good question, I guess. I think there are a couple of things going on. One is, I should say that the HOMO doesn't change for iron. So what that tells me is that depending on the energy of your metal that you put as an edge site, you're going to change where you are positioned in the electronic structure of the cobalt core. So the cobalt core has some states, and now if you pick iron, you're going to be pretty deep into the cobalt. You're going to first oxidize the cobalt a couple of times before you get to the iron. However, if you go to copper too, now that copper is going to immediately get reduced, and so you're going to change the order of your energetic levels. So that's the beauty of having this modular synthesis, and that you can change your edge site and change the relative energy of your edge site and cluster support.
Okay. Okay, thank you. And then how are the accepted spectra pattern of your synthesis materials in relation to the crystal phase?
Yeah. So that's the thing. The nice thing about these being molecules is that they are, we don't need to solve a powder pattern. So these are not, these are actual single crystals, So what this means is, it's like you take a precious stone. It looks obviously these are not that precious, although they are kind of precious because they cost a lot to make, but they're single crystals. So every molecule is in the same location. So, and the crystals are large enough that we can actually solve using, not using Rietveld refinement, but just, direct methods or whatever single molecule strategies to solve the structure that we obtain from X-ray data. We don't have to worry about the powder pattern in solving it. Yeah.
And then how is the role of the structure of metal cluster and the ligand in catalytic properties of your compound?
Mm-hmm. Yeah, so the metal cluster, there are two parts to it. There's a support, which kind of modulates the electronic structure essentially, and the edge site, which allow for molecules to come and bind to it. So that's our low coordinate active site. And that's the one that performs the catalysis. So the ligands, the organic ligands, they are also important because one, they stabilize the system. Two, they change the solubility and the stability of the cluster. And they can also make it more electron rich or less electron rich.
Okay, and then this is for once more. Chemistry.
So they're all in a gas phase. We use Gaussian for those calculations that I showed you. So they're in the gas. We generally include the solvent model, especially when we have an oxidized species, just to better,
Okay,
emulate.
So you use under gas condition for the calculation, right?
Yes, but we do use different solvation models.
Okay. You use synthesis, a lot of multimetallic complexes. How do you direct the reaction in the synthesis multimetallic complex in order to get certain multimetallic complexes cluster? Yeah,
so again, this goes to the deterministic synthesis. And so we're very careful about what cluster we choose to use, what aminophosphine we picked. And what's the length of those ligands on the surface of the cluster in order to give it the best chance to work. So we did a lot of work beforehand to give this system the best chance to work. Yeah.
Okay. Is it true that the ratio mole is one of the key to get the certain cluster that we want to get?
Yes, absolutely. Yeah, in general, for cluster synthesis, the stoichiometry of your metal to chalcogen or whatever other, depending on the cluster you have, the ligand in general, it really is a key ingredient to determining the size of the cluster. But it's not, there are a lot of complex processes happening in those cluster formation synthesis. So it's not always trivial to determine what that ratio is. It's oftentimes determined empirically. So trial and error rather than know from the get-go what you should use.
Okay. This is computational chemistry again. To use the formula IA equals to minus LUMO.
That's right. Yeah, ionization energy is essentially like, similar to the concept of a LUMO. So, yeah.
Okay, and then this is the last question. How big the possibility for the participant here, or maybe some of our lecturers who want to join to your group for their further studies, maybe for the master or PhD degree?
Yeah, so that's true for all universities in the U.S. You apply to the university for their PhD or master's program. The information is on our chemistry website, or any department that you might be interested in, and then there are steps to follow there. So you don't apply directly to a group; you apply to the program, and it generally requires recommendation letters, an essay, etc. So I think all those are detailed there, and that's the path through which any person can join a department to pursue a PhD or a master's. It's a centralized admission process. There's a committee that evaluates that, and then that's how that happens.
Okay, very nice answer and discussion, Dr. Velian.
Thank you so much for having me. I think I hear my daughter for the past 10 minutes. I think it's her bedtime. So I think she's getting really waiting for me to come back. But it was really a pleasure. Thank you so much for having me. And yeah, I really had a lot of fun answering a ton of questions. That's the most questions I've ever had at any presentation ever. So that's awesome.
Okay, so thank you. Now we are reaching to the end of this JKSA webinar series. So to audience, I would like to ask you to give a big applause for Dr. Alexandra Velian.
Thank you so much.
So once again, thank you for delivering the very interesting talk. Hope we have another chance to meet in another occasion.
That would be great.
Okay, and as a moderator, I also thanks for all audience for the questions and also very nice discussion during the webinar. So hope we can see you in the next JKSA webinar series. And good morning and have enjoy your activities today. Thank you.
Thank you so much. Thank you so much, Adi, as well.
Okay.
Bye-bye.
Thank you. Bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you.
Okay, thank you very much.
Thank you Pak Adi dan Pak.
Terima kasih Pak Adi, Pak Bashir.
Oke, sama-sama.
Thank you.
Matur suwun, matur suwun.
Oke, sami-sami Bapak.
Oke, selamat beraktivitas Pak. Saya izin live ya.
Oke, matur suwun.